Welcome, this is lecture number 30. In this lecture, we are going to talk about small signal model validation using MATLAB and time domain correlation. In today's lecture, we are going to talk about, first we want to summarize various small signal transfer function in buck and boost converters. Then I want to show you step by step procedure how to validate AC small signal model using MATLAB transient simulation. Suppose you have linear transfer function that we have derived in the previous class, and we want to see how accurate those models, right? We want to verify, and here we want to use a transient simulation. Okay. Then understanding effect due to poles and zero in small signal model, and finally understanding small signal transfer function and step transient response. So let us if we recall in our previous maybe past 2 or 3 lectures, we have derived the AC equivalent circuit, right? AC equivalent circuit of a practical buck converter, where in this circuit we can derive various transfer functions. We can derive input impedance, we can derive output impedance, we can derive audio susceptibility, we can derive control to output transfer function. So this is the small signal block diagram, and here we are interested in these particular terms, right? That means we have a supply perturbation, you can have load perturbation, and the duty ratio perturbation in case of open loop is an intentional perturbation. That means we have not closed the loop. So in that case it is also a perturbation, right? And how this all perturbation or individual perturbation can influence or affect the output, how it is going to change the behavior of the output voltage, okay, that we are going to see. We have derived input impedance like this, okay, and we will see delta S, which is a polynomial, it is a second order polynomial. We have derived audio susceptibility, again this polynomial is common, and we will see what are the alpha, what is ESR, what is omega p. We have also derived control to output transfer function, again this polynomial is common, we will talk about alpha soon, ESR also we will talk about soon. We have also derived output impedance, here alpha we will talk about, R equivalent is the RL plus R on of the switch, and we will also discuss about what is the ESR 0, and this is another 0 coming into picture, and this denominator which is a pole, second order pole. And this alpha is nothing but R plus R equivalent by R, okay, where R is the load resistance. Now ESR 0 is very simple, it is 1 by RC into C, where RC is the ESR, okay. Omega p is 1 by R plus RC into C, okay, and then omega L, R equivalent by L, these are all well known. The polynomial which is the pole is a second order polynomial which consists of the Q factor and the natural frequency omega 0. And what is omega 0? Omega 0 for an ideal buck converter is 1 by square root of LC. For a practical buck converter, it should be scaled by this term, and this term will be roughly equal to 1 if R equivalent and RC are close to each other, okay. But more or less this omega 0 is mainly 1 by square root of LC. Then the Q factor is this alpha, already have discussed, R equivalent we discussed, RC is the ESR, ZC is the characteristic impedance which is nothing but square root of L by C, okay, and this is the Q factor, and this Q factor is the one which causes the change in the peaking, that means the phase margin. If the Q factor is high, that means the peaking will be high, right? Suppose if you draw the gain plot, in one case it will be like this, if you go further in case it will go like this, okay. So this high Q factor, actually if the Q factor increases, and when we want to evaluate who decide the Q factor. So this is primarily the load resistance, okay. In case of a constant current load, if there is no resistive load, then Q factor are decided by only the parasitic and the characteristic impedance, okay. So in this transfer function, if you take a boost converter, again we can derive the input impedance, we can derive the output impedance of a boost converter. It is an ideal boost converter. Again it has a 2 pole second order system, Then if you take the audio susceptibility, we can derive, and these polynomials are common, and control to output transform, this also has 2 pole. But in addition, there is a right half plane 0. Okay, so right half plane 0. That means that is one of the major problem in a boost converter. The right half plane 0 will, and in this presentation we are going to talk about if a transfer function has a right half plane 0 or a 0, then how is it going to affect the response of the system? Because in our second order undergraduate control system course, we have studied like a normal transfer function. Starting point was omega n square a square plus 2 zeta omega n s plus omega n square. So, this transfer function we have studied, and you can write this transfer function, even earlier transfer function also. So, in this transfer function our zeta is the damping ratio, okay, and it is linked with the Q factor. In the earlier in a buck converter we talk about Q factor, right. Now, if we obtain the step response, we have studied in enough detail, maybe if we recall that the response will be under damped if the zeta is less than 1, but of course, it should be greater than 0, and it will be over damped, it is greater than 1, and it is critically damped is zeta equal to 1. So, we can get the transient response for step input. Now, if we add another 0 with this transfer function, suppose we had as 0 1 by os omega z, then how is it going to change the response of the system, that we want to see. Now, before we move forward, because we want to validate our model, whatever we have derived, whether those models are accurate or not, first we have to check, and that is why we are talking about the device under test. In fact, this test you can also carry in the experimental prototype also. So, how to check output impedance? So, we have to take a DC-DC converter, okay, and we know in the derivation of output impedance, what we have considered, it is the perturbation of the output voltage when we perturb an external current source, provided that for input open loop output impedance, the duty ratio perturbation, input voltage perturbation should be set to 0. That means, we should use a fixed input voltage and we should use a fixed duty ratio gate pulse. Then in this converter, that means if the power supply, in fact you can in lecture number 13 we talked about the output impedance of a practical voltage source, right. So, if you take a power supply from the laboratory and you want to check or measure the frequency or basically the transient response, or you want to measure the frequency response of the output impedance, what you can do? So, input voltage, that means for the power supply here, because only the terminal voltage, this terminal voltage will be, terminal points will be available. So, we can connect an external sinking load and we can slowly change the load either by a sinusoidal excitation, and we can do a frequency sweeping and then measure what is the output voltage, peak to peak, AC and this sinusoidal. That means, here in the load current, if we take load current, it will have a constant load current, and on top of that you will have a excitation, perturbation load current, which will be a sinusoidal excitation. And similarly, output voltage will have two components, a constant output voltage and a excitation. So, due to this excitation of this current, you will get an excitation in the output voltage, and by measuring peak to peak output voltage and measuring the peak to peak of the current excitation, then you can get the gain and phase plot, and you should also measure the peak to peak, the time shift, that means to measure the phase shift. So, here we are talking about output impedance, and we have already discussed the output impedance expression. So, what was the output impedance? We know that Z0 in more compact form alpha, then there are 201 by S omega ESR, and there was one more 0 S by omega L, and the whole thing divided by 1 plus S by Q omega 0 plus S square by omega 0 square. This thing we have already discussed. Now, we want to verify output impedance. So, in order to verify, we want to verify with whom? Because we derive the small signal model from actual switching converter. So, the response of the small signal model must be matched with the response of the actual switching converter. So, that means using actual switch simulation. So, we should not turn on the load, that means there is a load switch. Okay. So, there is a load switch, this is a load switch, right. So, we should not turn on for 2 milliseconds, let the converter reach steady state, because if you turn on the converter, even a practical converter or a simulated. So, initially the initial point for a practical converter, it is totally discharged, and in the simulation you can set some custom initial condition, but you need to provide some 2 millisecond time, so that the output slowly reaches to steady state. After 2 millisecond, then at the end of 2 millisecond, we need to identify what is the steady state voltage, that means what is the average voltage. So, this is the average voltage, I will say the average voltage at steady state, this is the average voltage at steady state. Now, the question is whether should we measure this in case of open loop, because it is a practical converter. Because we have discussed that practical output voltage, in case of ideal, we know that output voltage for an ideal converter will be simply D into V in. But in case of a practical converter, our D practical is nothing but what? It is nothing but D by alpha. What is alpha? Alpha is R plus R equivalent by R, right. So, the practical duty ratio is smaller than the actual duty ratio, that we have discussed in the DC equivalent circuit. So, that means our V0 practical should be D practical into V in, which is nothing but D into V in by alpha. That means we can find out without searching that. Okay. So, we can find out. So, now we will apply a load step up transient at 2 millisecond. Okay. Then we need to capture the time domain data, because this has the full data of the output voltage and we need to store at a V0 t. Next, because we want to verify the actual switch simulation with our AC small signal model. So, we have to first write down the transfer function, we need to obtain the step response, and generally step response, if you write in MATLAB, it will give a unit step response. So, you need to multiply scale. So, you have to obtain the step response for output of the output impedance. Then you have to multiply minus delta I0, because we have discussed what we have discussed, that delta V0 by delta I0 minus is our output impedance, right. So, that means if we want to write delta V0 t, it will be, suppose we apply a load step of delta I0, this term. Okay. So, then it should be minus delta I0, which is the step size, into Laplace inverse of Z0 t. So, Laplace inverse. Okay. That means whatever time we will get, the inverse Laplace if you take, and this Laplace inverse, because we need to do the step response. But if we want to do Laplace, you need to put S, because this step, if you take the step response, the Laplace transform, it will be delta I0 by S. And in MATLAB, we will see that it is nothing but minus delta I0 into step response of Z0, because it is the unit step response, that means as if you applied unit load step multiply. So, because this will have, because of this negative sign, this negative is coming. Okay. Next, after getting this, it is just the AC equivalent circuit. So, it will give the AC excitation, right, it does not have any DC. So, now we need to add amplitude offset with the step response that we obtain from AC simulation, right. Then we also need to add offset time, and we will slowly come to this point, and then we want to compare actual switch simulation and the result obtained from small signal model. So, let us go how in MATLAB, how can we verify small signal model step by step using transient MATLAB transient simulation. So, first I will go to the code. Before I go to the code, I am taking the MATLAB code. I have broken into multiple, like there are multiple line, but I have broken into multiple pieces. So, here we are setting the parameter. Initially, we are clearing up the screen, everything, closing all the plot. Okay. Now, we are calling Bach parameter. So, this parameter will load all the parameter like ESR, input voltage, output voltage, inductor, output, capacitor, everything will be stored. Time period and switching frequency is 1 by T. Now, this input voltage is we are setting 12 volt, although we have defined here, but if you want to customize with a different input voltage, you can call redefine here, and reference voltage 1 volt. This is our desired value, and it is we are going to check the open loop simulation. So, it is expected the output voltage will not be desired one in case of a practical converter. So, the ideal duty ratio will be D equal to Vref by Vin. So, if you check 12 volt is the input, 1 volt is the output, and our ideal duty ratio is D into Vref by Vin, D equal to Vref by Vin and R equal to 1. Then this R equivalent, you can see this R equivalent is here. It is nothing but the sum of DCR plus RDS1, and this alpha where it is written here, it is here, this alpha here. Okay. Next, what is the practical duty ratio? The practical duty ratio is D by alpha, and the practical steady state voltage will be, because ideal steady state voltage should be D into Vin, but since there are parasitic drop due to the DCR of the inductor and the RDS1 of the switch. So, the practical output voltage will be Vin into practical duty ratio, which is here, and here alpha is greater than 1 if R equivalent is greater than 0, and that is true. If you in case of ideal R equivalent is set equal to 0, in that case alpha equal to 1, but in practical alpha greater than 1. The next, because here what we want to show here, the modulator, that means what is modulator? Even though you are using open loop, but in order to generate duty ratio, we are using a control voltage, and which is compared with a sawtooth waveform. That means this is my control voltage, this is my control voltage which is here, and it is compared, this is my sawtooth waveform, right, this is my sawtooth waveform, and sawtooth waveform it has the value, this is my Vm and this is 0, and this is my Vm is set to 10 volt. Okay. So, in this case I set Vm equal to 10 volt. Now, this control voltage, once you compare with a sawtooth, that means if I draw here and if I use a different color, so this is my sawtooth waveform, okay, and if I use my control voltage here, this is my Vcon, then this will generate my duty ratio. That means this will be my duty ratio will be here. So, this will be my D into T. You can say instantaneous duty ratio, then it will be D. If it is steady state duty ratio, it will be capital D. Okay. So, this is implemented, the logic inside the trailing edge PWM is implemented here. Okay. So, this is the block which is implemented. Next, steps to verify small signal, the same thing we are going on. Define the pole parameter, because we have studied that what is our ZC is square root of L by C, it is here. Then we have studied the ideal one, if it is the ideal converter, the natural frequency is 1 by square root of LC, but in case of practical we need to multiply by this factor, that also we have discussed. So, this whole line is here, this line is here, and finally we have to obtain the Q, and which is nothing but here. Okay. So, Q. Now, so it is alpha 1 divided by, that means there is a -1 sign. Okay. Next, define poles and zeros. So, we have already talked delta P, which is delta P, which is nothing but S square by omega 0 square. So, it is 1 by omega 0 square, then 1 by q into omega 0 and 1, then ESR 1 by RC. So, it is simply set here ESR. Okay. So, ESR 0 is just a constant, I mean we do not have to bother about this ESR 0, and then pole is 1 by this pole, it is here, and the other 0 which is here, it is here. Okay, R equivalent by L. Okay. Now, next we want to verify, suppose if you want to write the control to output transfer function. So, numerator is common, right. So, sorry, what is numerator in the so numerator is what? It is V in by alpha into this ESR 0. So, this is the 0, and what is the denominator? Delta PS, it is there in the denominator, delta. So, this delta is nothing but this. Then GVD is, this transfer function is my GVD, this transfer function is my GVD, and what is my GVS? GVC, that is a control to output transfer function. So, this is my FM into GVD. Okay. Now, remember what is GVD? GVD is nothing but V0 perturbation by D perturbation, and what is GVC? Is nothing but V0 perturbation by V control voltage perturbation, and this is equal to V0 by D perturbation into D perturbation by V con perturbation, and this is nothing but GVD into FM. Okay. So, this term is FM and this term is our GVD. So, this is written here, Okay. Next, define output impedance. What is the output impedance expression? It is R equivalent by alpha, which is written here. Then it has it is a continuation, this line is a continuation. So, the first thing, if you multiply this quantity, what you will get? If you write down this, it will be S square by omega ESR into omega L. That means, the coefficient will be 1 by omega ESR into omega L, and this coefficient is the first coefficient. So, this is first coefficient. Then what is the second coefficient? The second coefficient will be here. If you take the second coefficient, 1 by omega ESR plus 1 by omega L, the polynomial will be S, and this is our coefficient, the second coefficient, and this second coefficient is this one. So, this one is our second coefficient, and third coefficient is 1, because if you multiply these two terms, it will be 1. Then denominator is delta P, which is nothing but this, and the transfer function is in the transfer function between numerator and denominator. So, there is output impedance. Then you can also write audio susceptibility, this term here, it is here, then ESR 0, it is here, then delta P, it is here, and then transfer function. Now, if we want to plot frequency response, that means we are putting some figure number, because there are many figures. First, we want to plot Bode plot of control to output transfer function, which is GVC. So, GVC, please remember, it is GVD into FM. Since FM, we have taken, what is FM? We have taken 1 by Vm, and in this case 1 by 10. So, this will reduce the gain. As a result, you can see the DC gain of this transfer function, the low frequency gain is very low, it is almost close to 0 dB. This is the control to output transfer function, which is GVC. Okay. And this point, if you see, what is this point? This is our 10 kilohertz, and here it will be roughly 11 and around 11.5 kilohertz. So, it will be around 11.5 kilohertz. Okay, sorry, 10 per 20. So this will be sorry, it is not, so it will be 20. That means we can take 20. So this is our 10 kilohertz, this point is our 20 kilohertz, and this point will be roughly like a 24 kilohertz or so, and this is a transfer function between this. Okay. Next, we need to check now load transient response, because we need to verify the load transient response. So here is the total simulation time. Okay. That means if I want to simulate, let us say if we want to simulate, I will apply the load step at this time. So this is my t step time, and this is my total simulation time, which I am calling as a t sim, total simulation time. So total simulation is 4 millisecond and applying step at 2 millisecond. Okay. Now you can take any kind of transient. Suppose you want to take a perturbation in the duty ratio, or you can take the perturbation in the load current. That means step change in the load current or step change in the input voltage, right. So whatever you do, since we are changing the load current, so we want to check the load transient response. So it is the output impedance we decide, because if you recall, the load current was, this is the output impedance expression, and in the small signal transfer function, if you operate under fixed duty ratio and fixed input voltage, the output voltage will be affected if you excite from an external current source. Okay, and that can be modeled using output impedance. The effect can be modeled using output impedance. So now here it shows the step response of the output impedance. That means this will show the step response of the output impedance. So this will show the step response of the output impedance, Laplace transform, then we have to multiply with the step size. Okay, and this is here the step response, and we are extending the time from, we have drawn, that means from the step applied till the final time. And since it has a negative sign, right, you see this line is exactly here. So as if this we have obtained using MATLAB, which is y of s, which is obtained like a step of z0 in MATLAB. So that means our V0 perturbation, it is the AC excitation, is minus delta I0 into y of s. So this is here. Okay. If we apply a positive duty ratio step, this quantity need not to be positive, because it is coming positive due to this symbol. Okay. Similarly, now we want to verify with exact switch simulation. So this is our block. Here we are using a modulator here. This is our control voltage which you can perturb, and this is our ramp signal, and if you have already seen the inside picture. Now here we are setting the DCM enable 0, that means we are setting synchronous DC-DC converter, because we have derived the model for synchronous DC-DC converter. You can take any arbitrary initial condition of the inductor current and the capacitor voltage. Then we are calling the simulation file. From the .m file, we are running the Simulink file, name as buck converter underscore open loop. Then we are storing the result, because this result is stored in the workspace, the time scaling, we are storing this data, all these things we have explained at the very beginning. Okay. Now we want to verify and then plot. After you finish this simulation, that means that these data are stored, right. Now we can use any of this data with the scaling time to plot it. So how to plot? So we want to plot by using, this is our plot command. I will explain what is this, but this response we obtain this AC simulation. You see this V0, that means V0, sorry, here it is V underscore 0 underscore AC. So this is the response, this is the response from AC small signal model. We have to add this response with the DC, so that to get the complete picture. And what is the DC? Because it is under open loop, so the DC operating point before the step is applied will be Vp, which is a practical voltage. And what is Vp? It is V in into practical duty ratio. And what is practical duty ratio? This is nothing but D by alpha that we have discussed. Okay, add it. And you also need to add offset time. This is the step time, and this simulation was from 0. So, you have to add. So, this is the offset time. That means, our AC model response will start from the step time. Before that, there will be no response, because you are only, it will only give the excitation when there is a step input, right. So, now simulation file from the actual switch simulation, whatever we have stored. In figure 1 we are plotting inductor current, and figure 2 we are plotting actual output voltage. So, now we want to check this device under test. So, fix duty ratio in actual. So, let us go to the simulation. So, here we want to first set, I have explained step by step everything. So, 10 ampere load step I am applying, and initial value of the load resistance is 1 ohm. Okay. So, let us run it. This is the Bode plot that I have already shown. It is now, if you grid on. So, let me write down here the Bode plot. You can say grid on. Hold on. Okay. So, it will grid on. Now, we need to plot using hertz, not in radian per second, and we should limit to, because our switching frequency is 500 kilohertz, and we want to plot from, let us say 100. Okay. So, this you have already seen. This is the GVC, not GVD, GVC. Okay. So, you need to increase the gain, you need to provide high DC gain in order to boost up, otherwise you have a very poor bandwidth. Okay. This is uncompensated loop transfer function. Okay, we will see that. Next, what is next? Now, we want to check the actual switch simulation. That means, now if we run the actual switch simulation, and I have explained step by step everything. So, where we have to capture the AC model, then we have to add with the DC offset. So, everything you see, I am taking the V practical that I have explained everything. Now, this is the simulation. So, the red color trace is the waveform which is obtained from AC model, AC small signal model, and you can see, if you keep on zooming, that represent the average voltage correctly. That means, if you take the average, more or less capturing the average voltage, it is going almost from the average value. Okay. And if you check the transient response, that means load transient response for an open loop converter, you see that our AC model, small signal model, is perfectly capturing the actual switch simulation. That means, you can see the actual switch simulation, it is perfectly capturing. All these models are perfectly captured. Okay. That means, for load transient response, our model is perfect. Now, you want to check the same thing for if we apply a supply transient rather than load transient. So, if we apply a supply transient, let us say we want to apply minus 6 volt, it is originally 12 volt, now it will change from 12 volt to 6 volt. So, naturally it is open loop, the voltage will dip, and we need to change here what is our audio susceptibility, GVG. So, this should be changed here, GVG, because we need to check, if you go back, if you want to check the output impedance that we have discussed. So, this part I have discussed, then I want to check GVD. Okay, let us check GVD first. So, GVD, what we have to do? I need to check this, change this, that means, I need to take a step change in the duty ratio. Okay, and then this should be GVC, and you need to delta V con, because ultimately this delta V, delta D will reflect a change in the V con. Okay. So, that means, we want to first see GVC, because we want to make apply a step transient to the duty ratio 0.1, and similarly we have to take delta V con, since you are taking GVC, and this is our delta V con, we have to multiply and just run the simulation. Now we are running, we are actually repeating the same process, but now this time we are trying to match with the control to output transfer function. That means, if there is a change in the converter voltage or maybe a 0.1 duty ratio, so how is it going to change? So, you can see there is a slight deviation, but it is acceptable, in the acceptable range. Otherwise, the red traces is going. So, I think it would be better if we just increase this width. So, maybe we can use 3. So, if we just rerun again, yeah, so it will be better. So, if you check go, so there is a slight deviation, otherwise they are matching quite nicely. That means, this control to output transfer function looks, it is perfectly fine. Now, we go for audio susceptibility. In audio susceptibility, we need to keep the duty ratio fixed, because we are talking about open loop audio susceptibility. No external load transient response, input voltage step we have to apply. So, initially it was 12 volt, now at 2 millisecond we will change from 12 volt to 8 volt. That means, it will come to, and this is a transfer function. Okay. So, audio susceptibility, what we will do? Now, we will go back, we will make a change in minus 4 volt, because now no duty ratio step is applied, and here it will be GVG, because audio susceptibility, and we have to multiply with delta V in. So, delta V in. Okay. Now, we are all set. Let us run, and if we check, now we are checking the result with audio susceptibility, where we have applied a step change in the input voltage. Originally it was 12 volt, and now we want to change to 8 volt. So, minus 4 volt step is applied. Now, if you go and zoom this waveform, it is perfectly valid. I mean, almost nearly they are matching quite nicely. Okay. So, we can assume that this model works fine. Okay. There is a small deviation, because in the audio susceptibility expression there is a duty ratio D. So, we have to change the duty ratio, update the duty ratio, okay, in order to match this. That is why a slight shift is happening. Okay. Because this duty ratio, because we have applied, here we have changed the input voltage, but we have kept the duty ratio constant. So, in this case, duty ratio is fine, because we have kept the same duty ratio, but input voltage has changed. When the input voltage has changed, in the actual converter, what will happen? If you keep the duty ratio, naturally the output voltage will get shifted. Okay. So, we have matched the all 3 response fine, and this is what I have already explained, minus 4. So, it is perfectly fine. That means, now we have learned how to verify small signal model using MATLAB transient simulation, and that we have done for open loop converter, and we will see in subsequent lecture we can actually match the closed loop response using transient simulation also. The next question will come to our mind. Now, we know that our model is good, we can move forward. Now, we want to see what is the effect of poles and zeros, because in the subsequent lecture, when we want to design the compensator, we should keep in mind what should be our desired transfer function or what should be our desired step response, right. So, for that we need to understand what is the response due to poles and zeros. If you take a first order pole, this is a first order system, right. Then if we apply an impulse response, then G of s, Y of s is equal to G of s, and this is the proper definition of a transfer function. So, the transfer function, because in many cases people define the transfer function is a Laplace input of Laplace transform of the output by Laplace transform of the input, but this may not be a very precise definition. So, the more precise definition of the transfer function is that the transfer function is the impulse response of a system. Okay? Here it is same. Next, if you want to see the transient response of a step transient response, now we applied an unit step input. If you apply unit step input, then output will be g of s by s, because this u of s will be equal to 1 by s if it is unit step. Then you can obtain by means of inverse Laplace the DC gain multiplied by this term. That means, at t equal to 0, the output will be 0, right. That means, I would say at t equal to 0 or y of 0 is 0, because e to the power 0 is 1, right. At t equal to, for limit t tends to infinity, e to the power minus omega p t will be 0. Okay. Then what is our final value? Our final value is simply k dc, or in the sense that this will be k dc into the input step size. That means, what is the input step size? In this case, the input step size was unity. So, the output will be simply k dc into 1. So, that means, if the DC gain is 1, then output steady state value will be 1. If the DC gain is 2, the output steady state value will be 2, and if it is 0.5, so that means this is a scaling factor. So, this is a DC gain, and that is determined by this particular gain. Now, we want to see what is the response of an overdamped second order system, because we often encountered this question, like we face this question, and we often interchangeably use that if two poles are widely separated, then the response of an overdamped second order system is primarily dominated by the dominant pole, and the dominant pole, the pole which is close to the imaginary axis. And remember that we are talking about two stable poles, and if it is dominated by the pole which is close to the imaginary axis, then that means it will behave like a first order system. But whether this transfer function response will be exactly identical to a first order system, because if you want to characterize experimentally a system which is an overdamped second order and a system with a first order, then how do you check by means of a step response in experimentally, how do you check their performance, whether the system is second order or first order? Definitely they will not be exactly identical, they will be close, there will be some difference. If you take the full y of s, again we can write down the full expression, and if you take the inverse Laplace transformation, because we are just keeping the intermediate stage, it can be written like this. Okay. Now, you see we have taken one pole k times omega p, another pole omega p, and if we set k equal to very high, that means this pole is a high frequency pole, right, pole, and this pole will be low frequency pole. This is our low frequency pole, right. So, not okay. So, this is our low frequency pole, and this is our high frequency pole if k is very greater than 1. Now, if k is very greater than 1, the two poles are widely separated. This pole is the far left hand side, and this will be our dominant pole that we have studied. That means, the response of the system will be primarily dominated by this dominant pole. Then we can write k by k minus 1 is almost equal to 1 and 1 by k minus 1 0. So, the response of the second order system can be approximated to be y of t, and you see this is same response of the first order system. That means, the approximate response of the second order system is almost identical to a first order system. Now, the question is whether they will be really identical or not, because if they are identical, then we cannot differentiate between a overdamped second order system and a first order system. There has to be something. Next, again we are rewriting this equation. So, this is the response y of 2 output of the overdamped second order system, and this is the response of the first order system. See, this is an approximate sense, not exact sense, right. Now, the next question, if you take d2y dt, okay, and if you find out, that means the original expression, I am talking about this expression, from this expression, and you set at t equal to 0. If you find out, that means you differentiate this response. So, this term will minus omega t come, minus k omega t will come, you will find this will be simply 0. But if you take this response and if you write dy1 t dt, and which is computed at t equal to 0, what you will find? You will find it is nothing but k dc into omega p, that is it. That means, at the beginning of the response there will be different, that means the derivative. That means, if you draw the response, that means if I draw the response, if I apply a step input, let us say I have applied a step input here, then the response of the first order system will be like this, it will be like this, okay, it will not touch, it will just go close, yeah, it will just go close, and the response due to the second order system, initially it will go and then try to match, they will match because they are identical. So, there is a difference, if you zoom out, there is a difference in their initial condition, and this is the initial response, there will be difference. Similarly, if you take the second order system response, then you can find out depending upon the damping ratio. So, you can draw the plot, we have studied this in the control system context. If you apply a step response, if the KDC equal to 1, here it is a unity gain, then you will find that, okay, like this, and if it is even overdamped, then even overdamped like this. So, depending upon the zeta. So, this way your zeta is decreasing, okay, that means it will be more poorly damped, okay, and this will be, you can relate this, the poor damping will eventually lead to poor phase margin. That means, if you want to shape the response of the system in closed loop control, we need to provide sufficient phase margin, so that we can cut down the overshoot undershoot, because those overshoot undershoot may not be acceptable, okay. And we have discussed in lecture number 13 that open loop converter has a high overshoot undershoot, in fact we saw just in the simulation result, but that is simply not acceptable. So, in case of closed loop, we have to reduce that and we have to keep within a very stringent limit, because this power supply will be delivering current to the digital processor, okay, where we make to maintain the output voltage of the DC-DC converter within the noise margin of the digital system, okay. Now, we have studied all this control system, because this is a transfer function for original transfer function was G of S, where input was U of S, and this was a box of output, where G of S we consider like a omega n square, a square plus 2 zeta omega n s plus omega n square. At this we have studied in our control system literature, right. Now, my question is, what will happen in this system if you add a 0? That means, this is my original system. Now, it looks like in the form of our DC-DC converter. In case of control system, we have studied g of s in terms of omega n square, a square plus 2 zeta omega n s plus omega n square. You can simply divide omega n square in numerator and denominator. So, you will get 1 divided by 1 plus 1 by what you will get? You will get omega n by zeta into s plus a square by omega n square. Okay. So, from here you can relate what is my q, what is my q. Our omega 0 in this case is nothing but omega n. So, you can relate all this. Okay. So, in this case, in our case, we have found that now we have another transfer function. So, this is a transfer function without 0, and this is with 0. Now, it can be written as this 0 into the original transfer function, this one, right. If y of t is the unit response of this, that means we have applied a unit step to this system, that means this is our system g of s, and we have applied a unit step here, and we want to check what is the response of this system. This is my input. Okay. So, then this is a unit step response. Okay. And y of z is a unit step response of, if you replace this with omega 0 t, then it will be replaced by y z of t. We want to check this, and it can be shown that the response with 0 is nothing but the sum of the response without 0 plus 1 by omega z into derivative of the response without 0. And this 1 by omega z term, which is coming from here, where this is our 0 location, that means our 0, which is nothing but omega z. And you say that if the 0 is, but this is a stable 0, it is a stable 0, that means it is located in the left hand side. If the 0 is very far away in the left hand, that means if the omega z is very greater than omega 0, that means this 0, if it is a complex conjugate pole, then the frequency will be omega 0, right. And if the omega z is far left hand side of the imaginary axis, then, or basically in the pole means far left hand side, that means the frequency is very high, high frequency 0, then this 1 by omega z in this case, then 1 by omega z here it become negligible. That means, in that case your omega z t will be approximately equal to omega t. That is why in most of the control system textbook we study only this transfer function without 0, because we assume even though there is a 0, that 0 is located far left hand side by means of closed loop control, or it is originally far left hand side. Okay. So, then the response will be almost identical. The next task, if the 0 comes close to the imaginary axis, if this is not the case, that means we are talking about the another case, if omega z is less than equal to omega 0, that means it is coming close, it is close, or rather I will say in the language I should say, if omega z is close to omega 0, it may be close, it may be slightly higher, lower, close, then 1 by omega z is not negligible. In fact, it can be quite large, and if the 0 comes close to the imaginary axis, this response will be very fast. Even if you take a fast order system, you can have overshoot in the response if there is a 0. Okay? Generally, we know the first order system, a single pole system, there is no overshoot because it is a over damped response. But in the single pole system, that means if you take one transfer function 1 by s plus omega z by 1 by s plus omega p, such system you can have overshoot depending upon the location of the 0. So, you can have overshoot and then it will decay down. Okay. So, that means we have understood that if the 0 comes closer, this 0 can inject this that derivative action and that can create overshoot. But what happens if the 0 in the right half plane 0, that means 0 in the other side, that means this is my right half plane 0. Same analogy, if y of t is the unit step response of g of s without 0, y z of t is the unit step response with 0, then the total response of the system with 0 will be the response without 0 minus 1 by RHP into this. Now, there is a negative sign. Again the same analogy, if omega RHP is very far, then this effect is negligible, it has no effect. But this is case 1 if, but if omega RHP is close to omega 0 or even omega 0, omega RHP is smaller than omega, that means it is now coming close to the imaginary axis, then this can be severe, that means this can be, in that case it can be severe. So, this will lead to an inverse response, severe inverse response. And if you take a boost converter, you will see this inverse response is reflected in the transfer function, okay, and we will see that. So, we will take an ideal boost converter and we want to run the simulation and show that what happens if we go to a boost converter. Okay. So, if you go to a boost converter, okay, so let us go to the boost converter. So, you can check that the boost converter, okay, just hold on. Okay. So, we are just showing one example of a boost converter, okay, and this is the simulation. I am just showing the response of the boost converter. Yeah. So, here I am just showing one example. There is a reference voltage transient, okay, and you can see, just a minute, if I just redraw this one, that means this figure. Yes, so you can see that this is a small signal response and this is the actual switch simulation. So, initially, I mean, we want to change the reference voltage, we have applied a positive reference step change. So, it should have increased from the beginning, but because of this right half plane 0, you see there is an initial undershoot, it is first coming down and then going up, okay, and this initial undershoot, depending upon the RHP 0 location, it can be severe. Suppose if I want to plot the same thing, suppose I actually now if I change the load current, that means I want to now change the load current, I am further increasing and I am not stopping it. Suppose let us now we want to use another color, let us say green color, and run it. So, again 1 by 5, see now it has become even slower, sluggish, because we are designing the converter based on the, this is just I am showing an example of a closed loop, and here I want to rerun, but in the plot command I want to use another color, let us say I am using what do I say earlier, a red color, okay. So, red color corresponding to this, and I want to show you. Yes. So, I want to run once more where this colors, green color should come evaluate. Yes. So, these are the two cases. The first one, if we take the blue one, where the right of plane 0, now the right of plane 0 location become farther, so it is even farther. So, it become much slower and this bandwidth becomes slower because of the, so that means we can simply compare without switch simulation from this plot, we can simply compare this plot. That means, if we want to do this is the case 1/5, and if we hold this same value with the red color, and if we change the load resistance to 0.2 and if we do 1/5. So, I want to show that because the second case the right of plane 0 is coming close to imaginary axis. So, I am using a the bandwidth of the controller is smaller. So, as a result, that means if you want to design a closed loop control, if the right of plane 0 comes close to imaginary axis, then it put a constraint on your controller bandwidth, and in the green case the right of plane 0 is coming close to imaginary axis. So, we have to slow down the system, otherwise it may be unstable. So, that is why the green color is much slower than the red one, and this is the effect due to the right of plane 0. So, we will say more detail because we will design voltage mode control boost converter, and we will show all this case study there, how to design the compensator so that we can get the maximum performance using voltage mode or current mode control in subsequent lecture. But one thing I can say that I have shown you the response due to the small signal model and the response due to the actual switch simulation, they are closely matching. So, with this I want to summarize that we have discussed like a model matching mechanism, we have shown some case study for transient AC simulation, then we have identified some practical limit and MATLAB simulation case studies were presented. So, with this I want to finish it here. Thank you very much.